So this is the Module 1 practice exam for discrete math. I'm not going to solve every single one of these problems because that would be a video that's way too long. And some of these I think you should be able to figure out by looking at the answer key, which I have posted. So I'm really just going to go through and pick some of the more complicated ones where I feel like I should explain my thought process. And those are the ones I'm going to focus on. So I'll start out here with number 3. It says complete a truth table. So truth tables are usually pretty straightforward. You pretty much always start with 2 columns, P and Q, unless there's more than 2 variables, in which case you start off with 3 columns or 4, however many variables there are. The one on the right alternates true, false, as many times as it needs. The one next to it is true, true, false, false, again, as many times as you need. In this case, we only need this many, we're done. After that, I'm just looking at the individual components of the rest of this phrase. So I see a not Q and I see a not P. So those are going to be my next 2 columns. I'll put not P, not Q. The order does not super matter. You would not be penalized for a different order. So not P is going to be exactly the opposite of P. Not Q is going to be exactly the opposite of Q. And then once I have that, I start combining them into these compound propositions. So I've got one that says P implies Q. So that will be one of my columns. And the other one is not Q implies not P. And then the very last one should always be the whole phrase. So I just want to quickly say that if you're missing a column in the middle, I don't care that much. I'm not so focused on you getting every single column in the middle, although it will help you. If you are able to break it down step by step so that each column is just one simple operation, you're less likely to make a mistake. But what I'm really looking at is I'm looking at these and this one. And as long as you have those right and you got some stuff in the middle, we should be good. So P implies Q. Well, if P is true and Q is true, we're good. If P is true and Q is false, that is the one case where it is false. If P is false, the implication is true no matter what. So this column should look like this. For not Q implies not P, I'm looking at this guy and then this guy. So I'm going to start just by saying if not Q is false, the implication is true no matter what. And then let's see. If they're both true, it's still true. So this one is the only one that is false. And now I go to my last column, and this is just a double implication, biconditional. So it says they're equivalent. And I can immediately see that in every column they are equivalent. True, true, false, false, true, 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 true. So this statement ends up being a tautology, not part of the question, but if it had asked, I could have said that it was a tautology. So I can clean it up just a tiny bit, but this would be the answer. So I'm going to skip 4 because it's a very similar process, just a little shorter. 5 is the same, 6 is the same. I will do one of these. Let's see. Let's do 8. 8 is probably worth our time. It's very similar. It's just going to be a little bit longer because we have 3 variables here. So we're going to have P, then Q, then R. But again, the one on the far right alternates true, false, true, false, true, false, true, false. The one next to it is true, true, false, false, true, true, false, false. And then P should be true, 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 false, 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 false. We need some horizontal lines to keep this one straight because there's a lot more going on in this one. Okay, once I have this set up, I'm going to start adding in all of my other columns. Let's see. You're welcome to bring a straight edge to the exam if you find that that is helpful. I'm not super picky about what it looks like, but as I said, I'm really just looking at the beginning and the end of these truth tables. So let's see. The next thing I see is P or Q. So P or Q. And then I see P implies R. And then I see Q implies R. And then those three statements are all ANDed together. Okay, all of these lines are slightly crooked, and that is going to bother me. Sorry. But all three of those are ANDed together. I think all of my lines are at an angle. Sorry, guys. Yeah, they are. Once I fix this, I was going to say, because three things are ANDed, I don't need to do it 2 by 2. I can just put all three in one. So I'm going to do that for my next column. It's going to be P or Q and P implies R and Q implies R. And then my last column is going to be that full statement. So I can just copy this. It's this whole statement and then implies R. All right. So first P or Q. Let's see. I'm looking at these two columns. If at least one is true, the or is true. So the only time it is false is when they're both false. Then we've got P implies R. I find it easiest to first look for whenever P is false, because that automatically makes it true. And then I go back and look, well, if P is true, then Q has to also be true. Okay, so the times it's false are these two right here. Then I'm looking for Q implies R, so that's these guys. Same process. The first thing I'm going to do is look at when Q is false. That makes the implication true. So Q is false, Q is false, false, false. Okay, and then if they're both true, it's also true. Okay, so that leaves, yep, true, false, true, false. That's the only time the implication is false. So there we go. Now I need to AND all three of these together. So if all of them are true, the AND is true. Otherwise, it's false. So if all three are true, the AND is true. Otherwise, it is false. So just to double check, I've got all three are true, all three are true, all three are true. True, true, true. Yep, should match. Okay. Now I'm looking at my last column, and I want to know if this implies R. So the first thing I'm doing is anytime this is false, the implication is true. Otherwise, both have to be true. So in this line, they're both true. This line, they're both true. In this line, they're both true. Okay, there's never an instance where this column is false, but R is true. Or excuse me, other way around. Sorry. Where this column is true, but R is false. That's the only time that the implication would be wrong. It never happens. So this statement is a tautology. Okay, I do want to do number 9 because it's important that you know how to use those propositional equivalences. So propositional equivalences is referring to things like De Morgan's law or distributing, or one important one is this. If you have P implies Q, you need to know that that's the same as not P or Q. And this is called the conditional disjunction equivalence. So those are the big ones. De Morgan's, distribution, and conditional disjunction equivalence. Beyond that, it's things like double negation, which is super intuitive. Sometimes I don't even necessarily write double negation because it's very obvious. So some things are really obvious. The less obvious ones are distribution, De Morgan's, and conditional disjunction equivalence. So the first thing I'm going to use is this conditional disjunction equivalence because I see in my first statement got a lot of conditionals. There are no rules that we can use with conditionals aside from this one. So I know that's what I have to do. So instead of Q implies R, I'm going to right away put not Q or R because that is equivalent. And this right here is my justification. So I would put this justification. Okay. From here, I still have an implication, a conditional, this arrow that I would like to get rid of. So I'm going to do the exact same thing again. And I'm going to say not P or not Q or R. And the justification is yet again conditional disjunction equivalence. Let's see. Next, I'm going to notice that this is a double negation. And instead of not P, I just put P. The justification is the double negation law. From here, well, let me look at what I'm trying to get to. Okay, I'm trying to get to this, and this is part of the reason why I wanted to make this video, because I'm going to show you, I would work this one a little bit backwards. My goal is this implication, but I know that I don't have any rules with implications, so the step before it must be this, not Q or P or R. Like, it's got to be this conditional disjunction equivalence. So let me actually write my final step and the step before it, because I know that I'm going to do that. That's the only way to handle, I'll just paste it because I've already written it. That's the only way to handle these implications. So I am just going to work backwards because I know that. I know that I'm going to have to use that. Let's see. Slide it over. Equivalence. Okay. So this is really my goal. I need to manipulate this to look like that. And the good news is I'm actually super close. I see that they're both ors. I see that I need P, not Q, and R. I've got all of that. It looks like the only thing I need to do is rearrange it using like associativity and commutativity. So the first thing I'm going to do is, well, let's see, I need to put P and R together inside parentheses. So to do that, I'm going to switch the order so they're next to each other. So I can put R and not Q. And that is commutativity. Commutativity, or commutative. It's just commutative law. I think that's what they call it. Then I can move my parentheses. So right now they're around R and not Q, but I can put them around P and R. And that is the associative law. And then I just switch the order, not Q or P and R, and that is commutative again. And those two are exactly the same, so I don't need this line. I have finished it. That is the same as what I'm looking for. Okay, so recap. 3 important ones that you should memorize, or at least use often enough that they're very familiar. De Morgan's, conditional disjunction equivalence, and distribution. Beyond that, I think it's intuitive. Things like this, not P is the same as P, should be mentally, hopefully very easy for you. Similarly, knowing that you can switch the order or move the parentheses around should be pretty intuitive. That works with multiplication and addition. It's very common. So those should be intuitive. The ones to practice are this guy and then De Morgan's and distribution. Okay, let's see. I don't think I'm going to do 10. I think y'all can figure that out. I don't think I'm going to do 11 or 12. I will do one of these. Let's see. So for 14, we've got a lot of different ones. I'm just going to do the first one. So it says P of X is the statement student X has taken class Y. And then it gives you the domain for X is students in your class. The domain for Y is computer science courses. Okay, so the first thing I'm going to do is I'm going to translate it very literally. So the first symbol says for any, and X has to be a student. So I'm going to say for any student in your class. We'll call it X. For any student in your class X, the next symbol says there exists. There exists a computer science course Y such that, just transition phrase. And then we've got P of XY. So that's student X has taken class Y, such that student X has taken class Y. But this language is super, super formal. So I like to always do a second pass where I rewrite it in much more conversational language. So this is saying, pick any student in the class. There is a computer science course that they have taken. So that's what I'm going to say. Every student in this class has taken a computer science course. You don't have to do both of these. The second one is really what I'm looking for. Every student in this class has taken a computer science course. But I strongly recommend putting both if you are looking for any sort of partial credit. If you're ever not certain about the way you phrased it, if you're not 100% positive, this top sentence will definitely give you partial credit. It's super formal, very structured, hard to understand. So the understanding is what I'm looking for, which is why the bottom phrase is what I'm looking for. I want to make sure that you understand what you're looking at. And this does not necessarily persuade me that you understand, but it is a very, very helpful step. So I recommend both. This is what I'm really looking for. B and C are very similar. I've posted the answer keys so you can check with those. Oh, let's see. Okay, I'll do 16. Do I want to do 16? Yeah, I'll do 16. Okay. The sum of two negative integers is negative. So we're supposed to use quantifiers, logical operators, predicates. Okay, so quantifiers are the for any and there exists. Two negative integers, that sounds like we're talking about any. So I'm going to say for any x. And I should say within, I may have messed this up on the answer key. For any x that is an integer, because we're specifically talking about integers. And for any y that is an integer, the following thing is true. If x is negative and y is negative, then we can conclude that their sum is negative. And that is pretty much what we're looking for. I believe I forgot this part on the answer key, so I'll make that adjustment, but it does specifically say integers, so we should specify for any integer x and any integer y. If they're both negative, then their sum is negative. I'm going to do 17 because I want to do De Morgan's with quantifiers. So this one says for there exists a y such that there exists an x such that the predicate is true. It doesn't tell us what the predicate is. But it's important to know that to move a negative inside, you change for there exists to for any. And let me quickly explain why. This statement says not there exists an x and y that make this true. In other words, there does not exist a single x or y that makes this true. I'm going to write that. In English, it says there does not exist an xy that makes, I'm just going to say such that makes P of xy true. In English, that's what we're saying. There does not exist one. So, in other words, for any x that you could possibly pick and any y that you could possibly pick, this is not true. As you move negatives inside quantifiers, there exists becomes for any, and for any becomes there exists. So that's really the answer that it's looking for. You could do this one step at a time, but the main point is when you move the negatives inside, it switches. I'll briefly look at 18. So first I want to read this statement. It says, find a common domain for x, y, and z that makes this statement true and another that makes it false. Okay, so it says for any x and any y, they have to come from the domain. If they are not equal to each other, then pick any z and z equals either x or y. So if x and y are not equal, then any z in the domain either equals x or it equals y. Any z in the domain. So the only way this works is if you have two things in the domain. It could really be anything. It's just a set with two things. So like 0, 1, for example. If x does not equal y, then that means we've either got x is 0 and y is 1, or vice versa, y is 0 and x is 1. Those are the only two options. And in that case, z must be either 0 or 1. It makes this statement true. So it's true for any domain with only two elements. Makes the statement true. I'm going to say, or any domain with, technically I think it could have one element, so I'm just going to say any domain with at most two elements. And then it's false for any domain larger than that. If you've got a domain with three elements, x, y, and z could all be not equal to each other. Okay, number 19, definitely worth doing. It's kind of lengthy, so let's take a moment and look at it. It says C of xy means that the person X has chatted with person Y. Okay, there is a student in this class who has chatted with exactly one other student. That's the first thing we need to do is write it using quantifiers. So, okay, there is a student. Easy enough. I'm going to start with there exists an X. And then they need to have chatted with exactly one other student. So I'm going to start with, that means there exists another student who they have chatted with. So C of xy. The hard part of this is the exactly one. So they have chatted, but also they haven't chatted with anybody that's not Y. So I'm going to say, if you look at any other student in the domain for any Z, if Z is not the same as Y, then Z has not chatted with X. So let me say that again. This first part just says X has chatted with Y. But I needed to focus on exactly one. That means if you look at any other student in the class, if it is not Y again, X has not chatted with Z. That's what makes it unique. Now, I do want to make a note. It is definitely possible to simplify this, not write all of this, and just put exists unique Y. And if your only job was to express the statement in quantifiers, that is the way to go. The reason I did all this other work is because I'm going to have to form the negation in just a moment, and we don't have a good way to negate this operator. So there does not exist a unique is very hard to negate. It's not a rule that we've learned in this class. It's not a rule we will learn in this class. So I don't know how to negate that, so I'm going to avoid using it. Quick note, I do think the textbook includes like another thing here that says X does not equal Y, like it's chatted with one other student that's not themselves. Why did I leave that off? I probably shouldn't have. I probably should have included it. It's just a pretty small part and it makes the statement really long and tedious. So it probably would be good to include the fact that X does not equal Y, but that's just not what I'm looking for when I'm grading. I'm looking for like general understanding. And that's pretty technical. So I'm not going to be picky about it. But if you include it, that's great. Okay, the next thing we're supposed to do is form the negation of the statement. So the negation of the statement, whoops, is the exact same thing. I'm just going to copy it. Okay, so there's the negation. And then it says, so that no negation is to the left of a quantifier. Okay, so we have 3 quantifiers. The negation is to the left of all of them. So we need to start moving it. So the first thing I'm going to do is move it past the exists. And if you remember, that changes them into 4 any's. So now it's here inside of my and statement. Let's see. I think I should have this bracket right here. That's just going to be a little clearer. Yeah. So it's it's outside of my and statement. And if you remember De Morgan's, to move this negative inside of the and statement, the and is going to become an or. So I'm going to have for any x and for any y, this is just a simple negation, and then this becomes this. Okay, I think that is it. Next, I am going to move this negative past the quantifier, which changes the for any into there exists. So for any x, for any y. All of this is the same, except my next quantifier right here becomes there exists a z. Okay, for the record, I technically have finished this part. So I could write it in simple English as it is. But in the answer key, I did a few more steps just because this part is hard to understand. It's hard to know what it means that something is not implied. So to fix that part, I ended up changing it using if you remember, P implies Q is the same as not P or Q. So I wrote that. So we've got, instead of Z does not equal Y implies this, I put Z equals Y, or this, not CX, Z. Because that just is going to make it a little bit easier to translate to English. So not a required step, but it is easier to translate. Okay, finally, I'm going to distribute this negation, and that is using De Morgan's because it will change my or to an and. So there exists a z such that z does not equal y, and not. There we go. Okay, now this is actually much, much easier to understand in English. So I'm going to translate it now. So this says, for any student X in this class, I'll write it. In this class. And for any other student Y. Option number 1 is they have not chatted. Either They have not chatted, or there exists some other student who is not Y that has chatted with X, or there is a third student who has chatted with X. And we can double check that this is logical. So our original statement said there is a student in this class who has chatted with exactly one student. My concluding should be the opposite of that. And I said every student in this class either has not chatted with every other student in this class, or they've chatted with Y and Z. And that is exactly the opposite. That means there is not a unique one other student. There's either zero or multiple. So it's logically consistent. It was a good negation of my original statement. So again, the final answer for the quantifiers part of the question is this right here. This is a perfectly acceptable final answer. The only reason I did those additional 2 steps was to make it easier to translate into English, because it's very hard to mentally understand a not implication. That's just kind of tricky. It gets much, much easier if you can change it into the change it into an or statement and then distribute that negative. It just gets easier to understand. Not a requirement. It does kind of verify that your final answer will be easier to understand and a little bit easier to verify that it's logical. So hopefully that makes sense. If it doesn't, send me an email. Let's see. I do want to do one of these. I think I want to do this third one. Yeah, 22. Okay. 22 is kind of long. So the first thing I need to do is I need to give these hypotheses letters. So I just didn't have a lot of room, so I put it up here. I think R is it rained. So that's the first statement I see here. So it rained. And then F is it is foggy. And then S is the sailing race will go on. And let's see, the life-saving demonstration, I'm going to do an L. The life-saving demonstration will go on. And then I need one more. Trophy was awarded. Trophy was awarded. So with these arguments, you pretty much always start by writing out the hypotheses. So the first hypothesis is, if it does not rain, or if it is not foggy, then the sailing race will be held and the life-saving demonstration will go on. Okay, so that's the first one. The second one says, if the sailing race is held, then the trophy will be awarded. The third one says, trophy was not awarded. Okay, and our goal is to get to our goal is to get to R. It rained. Okay, well, the first thing I noticed right here is we've got S implies T, but not T. And if you remember, that leads you to draw the conclusion, not S. If S leads to T, but T didn't happen, then S couldn't have happened to begin with. And that is a modus tollens. All these others are given. So this one's given, given, given. Let's see. My goal is to get to R. Okay, I see a pattern here. I have not S, and I'm looking at this guy right here. If S is false, then I know that that whole thing, S and L, is false. So that's actually the next thing I'm going to write. S and L is false. So that's true just by the definition of and. So that's what I'm going to write. The definition of and. If S is false, then S and L is false. You don't need to know anything about L to draw that conclusion. And that's helpful because that is the conclusion of this conditional. And if the conclusion is false, then the original is false. So I'm going to draw this conclusion, or I'm going to put this statement next, not this guy. So if this is false, then this must be false. That works with every implication. If the latter is false, the original must be false. And that is by Modus Tollens. It's the same strategy. From here, I can distribute this negative using De Morgan's. That gives me not R, and not F. De Morgan's. Then got a lot of double negations there, so I can take care of those and just say R and F by double negation law. And that is enough to conclude R. If R and F is true, then R alone is true, and that's just a simplification. You could also write definition of and here, but simplification, I think, is what it's called. But that should do it. I've been able to reach my conclusion using the rules of inference. I will say there's probably multiple ways to do this. There's a lot of different steps you could take. And as long as they're legitimate and they get you to the right conclusion, the exact order doesn't matter. So hopefully that makes sense. If you wanted additional clarity, whenever you use these like Modus Tollens, it helps if you like say which statements they came from. So like I used 2 and 3 to conclude number 4. And then with this guy, I think I used 1 and 5 to conclude it. So I like to put those in there just to be absolutely clear what 2 statements I combined to get to my conclusion. Okay, I want to do number 23 because it's another one that I just don't think is super intuitive. And let me say this, for some of these proofs, it requires some creative thinking. And if the thinking is too creative, I'm going to give you a hint on the test. 23 is a great example of this. If I were you, I would try to wrestle with it first. So if you haven't wrestled with it, pause the video and go think about it before you watch my solution. On a test, if it's a question like 23, I will almost certainly give you a hint. 24, 25, 26 don't need hints. Those you should be able to do. It's pretty straightforward. But 23, and I think it's the very last one. I think it's 39. Yeah, 23 and 39 are the hardest proofs on here. And they're to the point that if I put something like that on the test, I will give you a hint. So I'll just give you the hint right now. What I would say is something like this. I would say, hint, consider I'm going to say use the definition of a perfect square. Hopefully you know what that is. And consider the next largest perfect square. Next largest perfect square. Okay. A perfect square, if you don't remember, is just a number that has a nice square root. So 4, because the square root is 2. 9 is a perfect square. The root is 3. 16, which the root is 4. So the first thing I need to do is I establish that n is a perfect square. So n is equal to something squared. And I need to specify where k is I think I can make it non-zero. K is a non-zero. No, excuse me. Non-negative. Non-negative integer. And really, it's a natural number. But that makes it a perfect square. From here, let's see. Actually, I think I want it to, I just want to say it's positive, where k is a positive integer. That does eliminate the case of 0, but I can prove 0 separately. So if k is 0, then n is 0, and n plus 2 is 2, which is not a perfect square. So I know that I don't have to worry about the case of 0. I could prove that separately. I'm not that worried about it. So I'm going to focus on when it's not 0. I'm going to make k positive. So that's the definition of the perfect square. Then it says, consider the next largest perfect square. Well, the next largest you would get by taking k plus 1 and square it. So k plus 1 squared is the next largest perfect square. And from here, I can just do some manipulation. K plus 1 squared, I can FOIL. That's k squared plus 2k plus 1. And k squared, well, that's just n. So this is n plus 2k plus 1. Okay, so my goal is to prove that n plus 2 is not a perfect square. And I'm noticing that this is definitely bigger than n plus 2. Because we said k has to be positive. So this is bigger than n plus 2, which means if the next perfect square is bigger than n plus 2, then n plus 2 cannot be a perfect square. Because we said n is the one perfect square, and then n plus 2k plus 1 is the next perfect square, the next one up. We skipped right over n plus 2. So we can't have n plus 2 as a perfect square. I'll say again, this is one of the harder proofs on this practice test. I don't necessarily expect you to be able to solve this one start to finish on your own. I do want you to try it and wrestle with it. And I want you to try and wrestle with number 39. But some of these other ones where it's like 24, 25, 26, those are more likely to be on the test. That's a little bit more the level that I would expect you to be at. But 23 is a great exercise. I'm going to skip 24, 25, 26 because they're on the answer key. They're not hard to understand. You should just give it a shot on your own and then look at it. Let's see. I think a lot of these are pretty straightforward. And if you have access to the answer key, you should be okay. Which ones do I want to do? I did 35 in class. So 35 is a good one, but I have the notes from class. They're posted. Okay, I want to do 36. 36 is good. Okay, so determine if the following functions are injective, surjective, or bijective. Injective, if you remember, means one-to-one. So one input to one output. One input per output. That's what injective means. Surjective means every output can be achieved. So every output in the range can be achieved by the function. Bijective just means both injective and surjective. So all of these functions, you'll notice, go from the natural numbers to the natural numbers, which means we are starting with 0 through infinity, and they've got to be whole numbers. So let's think about injective, n plus 17. Well, Easiest way to consider this is think of the picture. So it's a line. It's a line that kind of looks like this. Of course, if we're just going to end, then it's just dots. But it would pass the horizontal line test, which makes it 1-to-1. So this one is injective because each output is achieved by a unique input. How do I want to phrase that? Each output, I'll call it Y, has exactly one input. And I know what the input is. The input would be Y minus 17. So if you plug Y minus 17 into the function, you will get Y as your output. There's no other possible way to get Y, so it is in fact injective. However, if the lowest we can start with is 0, the lowest output we're going to get is 17. So it is not surjective because it does not touch anything below 17. Now you only need to give one example because 0, for example, is not a possible output. There is no number you could plug in. There's no natural number you could plug in to get 0 as an output. And that means it is not surjective. Let's look at B. Option B is a floor function. So you take an integer, divide it by 2, not just an integer, a non-negative integer. It's got to be a natural number. Divide it by 2, and then the floor function means you round it down. So, for example, if you took 1, a half rounded down is 0. But you could also plug in 0, and 0 rounded down to the nearest integer is also 0. And that means it is not injective. So it is not injective because, for example, 2 different inputs can give you the exact same output. So 1/2 rounded down is 0, but also 0 rounded down is 0. So it is not injective. Let's see. It is surjective, though. It is surjective because every integer, every output, Y, is equal to, you can get any number greater than or equal to 0 by taking a number greater than or equal to 0, dividing it by 2, and rounding down. You can get 0 by plugging in 0. You can get 1 by plugging in 2. You can get 2 by plugging in 4, and so on. So it's equal to this for some natural number n. Okay, C is neither. C is not injective because f of everything is 17. F of 0 equals f of 1 equals f of 2 equals ... It's not unique by any means. But it is also not surjective because no outputs can be achieved except y, because 0, for example, is not a possible output. The only possible output is 17, which means it does not at all cover the whole range. Okay, this last one has a subtract 17. So if you plug in 0, you get negative 17. Let me write that. If you plug in 0, you get negative 17. That is a problem because negative 17 is not a natural number. So this one is actually contradictory. You cannot have a function from naturals to naturals defined by this because the domain doesn't work. The domain does not give you a natural number. So I'm just going to say this one is neither because it is not a function from n to n. It's kind of a tricky one. I probably wouldn't ask you something like that on the test. I would ask you something like a, b, and c. Okay, 37 I think is pretty simple. The answer key is very thorough on that one. Same with 38. I think it's pretty straightforward. I do want to do 39 because, like I said, it's one that I don't necessarily expect you to figure out how to do on your own. It's more of a challenge question. So again, if something like this showed up on the test, I would give you a hint. I'm not sure exactly what this hint would be, but I'll tell you how to start it. The hint would give you some clue or indication that you should do this. You should let x equal, well, let's see, we're doing a ceiling function, which means it's rounded up. So we're going to round it up here. We're going to round it up here. So that means x could be just below an integer. So x should be some integer minus a little bit. So I'm going to make k an integer. And epsilon is like less than 1. It's between 0 and 1. So the function is an integer minus a little bit. A little bit could be 0. It could be anything up to 1. But x is an integer minus a little bit. And that's really the hint. Okay, so if you can do this, then let's see. Then rounding x up should give you k. And that's just by the definition of the ceiling function. By the definition of the ceiling brackets. Then, okay, let's take a look at x plus m. Well, that's equal to k minus epsilon plus m. And it said m is an integer, so I'm going to put my integers together. K is an integer, m is an integer, epsilon is a little bit. So I could actually put parentheses right around here. That's an integer minus a little bit. Rounded up, we get k plus m. And if you remember one line ago, I wrote this. K is the ceiling function of x. And that actually does what I want it to do. I said that the ceiling of x plus m is equal to the ceiling of x plus m. And that is the beginning and the end of this line. So those first two really, you have to think creatively about it. This first one is where I would give you the hint. You would have to kind of figure out line 2 that the reason the hint is useful is that it's easy to define the ceiling of x. The last line is what you would be expected to do on your own. You would need to know how to manipulate this ceiling function to change this into this. One last comment before I wrap this video up. In my opinion, proofs are the hardest thing on here, but the proofs you should expect are something along the lines of, where were they? There they are, 24, 25, and 26. So I would definitely practice those without looking at the answer key. See if you can really understand how to do that. And if you can do those, you're in good shape. If you figure out 23 and 39 on your own, then you're in very good shape. But those are really challenge problems. All the others in here are pretty realistic. Those two I would consider particularly challenging. So good luck. Send me an email if you have any questions, and I will see you Monday for the test.